Welcome everyone to another Leetcode problem. Today's problem is problem 36, valid Sudoku. So if you're not familiar with the game of Sudoku, let me introduce you to the game. So it's a 9x9 board game. So this is an example of a Sudoku board. And what you have to do is you have to fill up each of these cells with a value from 1 to 9. So this is a partially filled up Sudoku board, and this is a solution for that. So what you have to do is you have to put the numbers and make sure that none of the rows have any, like all the rows have numbers from 1 to 9. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of the rows have the values of 1 to 9. And also each of the columns will also have the values from 1 to 9. Okay, so any column you check will have the values from 1 to 9. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay. Not only that, also you have to make sure that each of these 3x3 boards also have the values from 1 to 9. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So now it's important to know that like all Sudoku boards are not valid. So say you are given such a board, and if you start filling this up, say, let's say if I put 5 here, this one becomes an invalid board because as you can see, this block has now 2 5s, right? So that's not allowed. Or if I put a 4 here, right? Let's not put a 4. Let's say put a 4 here, okay? So it looks like there is no 4 in this row. That's fine. But there is 4 in this column, so that's duplicate. So that is invalid Sudoku board. So what we have to do is we have to find out we'll be given a Sudoku board. It might be like a full board, or it might be a partially filled up board. So if it's not filled up, then the empty cells are going to be denoted by these dots, and the filled up cells are denoted by any number. So given that board, we have to find out if that's a valid one or not. Okay, so that's our problem. So how do we solve this? Okay, so obviously, as you can see, we can actually check each of the rows, right? And see if there is a valid, uh, if there are duplicates in that row. And then we can similarly check each of the columns and then check if there is any duplicate in that given column, right? And then we can also check each of these blocks and see if there is duplicate in that box. So what is a very good data structure to do that? Obviously, we can use hash sets, right? Because in hash sets, every element is can be present only once. So we can keep on adding to the hash set and see if we try to add to the same hash set which already has the value, then we can say, okay, this is not a valid one. Okay, so let's think a little bit more formally. So this is given a board, and these are the like the rows. As you can see, these are the row numbers, and this is the column numbers, right, for the ease. Okay, so what we can do is we can have a hash set of size say 9, right? So this is our hash set array of hash set. Okay, so each of these are one set, right? Each of these are one set. So this is say the hash set of column, right? Okay, so what we can do is we can just keep on reading here and add to the specific index set. So this is index 0 set, index 1 set, right? Index 2 set. So we read 5 and say we read 3, so it will go here, right? Okay, so we keep on doing this. Say there was another 3 here, right? So if I try to add this, it will be added here, and then there'll be conflict, right? And then immediately we can say this board is not valid. Similarly, for the rows, we can have another array of hash sets of size 9, right? So each of these array sets are going to represent each column. So this is this is hash set, array of hash set of size 9. Okay, so let's call it column. So this is going to be column 0. This is going to be column 8, right? So each of these are hash sets. So we read from here, we read 8, we add it here. Say if we read 6, we add it here. And then for each of these sets, we will keep on checking conflict. So say if there was, say, another 6 here, right? Another 6 here. Then as soon as we read it and try to add it here, and then there'll be conflict. So we are done. Okay. So it's easy. Like each row 0 is going to be like whenever we're reading from row 0, any element from row 0, we'll add to these hash set, right? Whenever we are going to read from, say, column 1, right? So for these element, this is going to be added to the set hash set for columns at index 0, and hash set, sorry, this is not column. I made a big mistake. This is row. Sorry for the confusion. This is the row set, right? Okay. So once we're reading this 3, we'll be adding to the row set of index 0 and column set of index 3. Okay. So another one more time, I just made this mistake. I just mentioned them as column. This is should be row. Okay, so there goes our checking of. So that means we can have a hash set of size 9, right? Of size 9 for the rows, and another hash set of size 9, hash set array of size 9 for the columns. Now, what about the boards or blocks, right? So how do we check each block? How do we make sure that these element and these element stays in the same block? Well, let's see. Can we denote this as block 0? This one as 1, this as 2, this as 3, 4, 5, 6, 7, 8. Yes, we can intelligently do that. Let's see how can we do that. So as you can see, if this one has row index is 0, 1, and 2, right? But if we divide this index value with 3, we get 0 for all of them, right? Similarly, for these 3, this, and this, if we divide them by 3, we get 1, 1, and 1, right? Okay, so there goes that means if we divide the value of row index by 3, we get these values, right? We get these values. Similarly, if we divide the column values with this, then we get column values with 3. If we divide by 3, then we get these values, right? We get these values. Okay. Now let's say if we read this, if we're reading this is row 2. So let's say row over 3. So this is row 2 and column 4, right? So this is column 4 and row 2. So this, okay. So it will be like 2 by 3 plus 4 by 3, right? So it will be, okay. So if we do it by 3 into this, so as you can see, 3 into 0 plus 1. So this is going to denote 1. So this is board 1, right? So our formula is going to be 3 into row index by 3 plus column index by 3. Okay. So let's see for this one. Row index is 6. So it will be 3. So for this one, 3 into row index is 6 by 3 plus, and the column index is 3 here, right? Column index is 3. So it's going to be 3 into 3. As you can see, 3 into 2 plus 1, which is 7, right? So this one denotes block 7. Okay, so this is a simple formula to get which block you are in. So now we can have a hash set for blocks, right, of size, hash set array called blocks of size 9, right? Okay, so here is one thing. So we will just read through the whole board, right? We'll read through the whole board, and then whenever we're reading something, we know which column it belongs to, which row it belongs to. So we'll add to that specific row denoting hash set, column denoting hash set, two of them, right? And then also we'll calculate the block from this equation, and then we'll add to that hash set as well. So we will need three hash set arrays of size 9, and we'll keep on adding. We'll read uh, one after another. We'll read the whole board, and for each value, we'll add it in 3 hash sets. And whenever there's a conflict, we'll just return false, right? That means it's not a valid hash set. It's not a valid Sudoku board. Okay, so let's check the code. As you can see, we have this 3 hash set arrays of size 9. I name them row, column, and box, right? Each of these boxes. And then what I do is I just initialize. So this is still null, right? So I just initialize each of these with a new hash set, right? So I run a for loop from 0 to 8 and initialize 9 of each these hash sets, right? Okay, next what I do is I read the board. So for row, I will go from 0 to 8. And then for column, I'm going to go from 0 to 8. Okay, so that means I am reading each of the values. So first I will check. So first the value would be 0, 0, right? So that means I am reading this 5. And then I will check if this is a dot, that means empty. If it's a dot, I don't do anything. Otherwise, what I do is I check if that particular hash set for that row already contains this value 5, right? So if this is row 0, this is so the hash set would be like this hash set at index 0. If it already contains 9, then I return false. Otherwise, I add this one to add the value 5 to row 0. Similarly, I add the value 5 to column 0 hash set, right? And if it already had this value 5, I would have returned false. And then I will calculate the box number. And I showed you the formula in the explanation. So I will do the same thing. I will see if the hash set denoting that box already contains the value. If not, I will add it, right? I will keep on doing this. So finally, if I reach here, that means there was no conflict in any of the rows, in any of the columns, and in any of the boxes. That means it was a valid Sudoku board, so I return true. Okay, so what is the time complexity of this algorithm? As you can see, we have this like we have this uh, 3 extra memory maps, hash sets, and each of these can have like 9 values, right? So as you can see, if this is a m into n, this is an actually n into n matrix, 9 into 9, right? So the amount of memory that I need is order of uh, n is order of say n square, because in the worst case I have to like put all the values in this array, in this array, and in this array, right? Order of n square, or you can say just we need constant like 81 places to store. That's the first thing. And the second thing is what we have to do is we have to just read these nested, like we have to read each value of the board. So if the size of the board is n into n, then we are just reading each element just once and adding to the set, or that's all about it. So it's order of, depending on how do we call it, whatever element it is, just we read each element just once. So if it's an n into n board, it's order of n into n. Or maybe we can say that it's an order of n if you think that the whole number of elements is n. In that case, It's an order of n algorithm. Okay, thanks everyone for watching. So we'll come back with another problem next time.